All right, dude, we are live. What's up, guys? This is Dem Keys, and today we are going to continue learning about clap. But hopefully, I'm going to finish learning about clap, and we're going to then kind of bridge the inquire and clap knowledge together and try and make something out of it. Um, I did not finish having that conversation with Gemini yesterday. Give me a second. Okay, yeah. I did not finish having that conversation with Gemini yesterday about where Gemini was explaining how this um, how the clap code works. Where is it? It's not this. It was here. What was I doing here? Here, I think I was just trying to. Uh, oh, here actually, I was trying to. Wait, I think we are doing that. I think we are having that. Little freeze issue. So give me a second while yeah, let's do it from here. Okay, now it's working fine. For some reason, okay. All right. Well, what was I saying? Yeah, I was going through this code yesterday because I was trying to understand how collect is working. Going back to the blanket implementations thing, I was trying to understand how collect is working. And sorry, give me a second. Yeah, I'm having a bit of issue. Well, okay, fortunately, the issue that I'm experiencing, you guys won't be affected by it. You won't be seeing it because I'm experiencing that issue on another machine, um, from which I'm SSH'd into this machine. But yeah, okay. Anyways, so um yeah, let's continue reading about how these various options are working. Yesterday, from what I remember, we had discovered that if it's an option, because the CLI struct is sort of the I think Gemini called it top level struct. Um, so within this struct, you can define what the various arguments and subcommands are going to be. And um, in terms of arguments, if an argument's type is option, then it's going to be an optional argument, means you can and also cannot give it, like you can choose whether you want to give it or not. And there can also be required arguments. I'm not sure what the other version of that would be. Mandatory arguments. Basically, these options are, or these arguments are required. So for example, if I, hold on. Yeah, if I called this and didn't give any arguments, then it would say the following required arguments were not provided. Say something is one of the required arguments. Whereas if I gave it something, it wouldn't complain, right? If I gave it two things, it would happily accept it because the second one is going to go for the second argument, which is a positional, sorry, which is an optional argument. Positional as well, kind of. I don't know if I would still call it positional at that point because it seems like the you have the required arguments first, then you have the positional arguments, right? What if I defined it in this way? Let's say um I don't know, let's just say arg02 and yeah, let's make sure The hints are shown and diagnostics are shown. Okay, now what happens here? Panic. It panicked because name was not provided. Now, was name the optional argument? Yeah, so we have CLI dot name. Name is the optional argument, and name is not provided. Okay, why did this throw an error? Found non-required positional argument with a lower index than a required positional argument name. Wait, found non-required positional argument with a lower index than a required positional argument. Name index is 2. How is names index 2? Found non-required. Okay, so I'm kind of confused here. Okay, name would be non-required, right? I'm assuming this is the problem. So if I run this, yeah, everything works now, right? Now I'm confused about that index 2 thing that was mentioned. So I'm going to ask Gemini what is going on here. Okay, I need to copy this entire um hold on. All right. Oh God. Okay, I need to do it on this machine. Right, let's try that again. Okay, hey, wait. Hey, I'm learning um about the clap crate in Rust. Explain to me why um the following the following struct or the following organization of fields gives an error. Let me also mention, oh, wait. Uh, Let me also mention that I have copied this code from tmux, so there, from tmux, no, from neovim running in tmux. So there might be extra characters in there. Also, the error I get is actually a panic. Here it is. Okay, let's copy that. Actually, you know what? Let's copy this entire thing. All right, let's see what Gemini says. And in the meantime, let me also open up my stream on my phone So I have the chat open. Okay, sorry, I got distracted for a second. Okay, the panic message tells you exactly where you went wrong, exactly what went wrong. Found non-required positional argument. Found non-positional, no, found non-required positional argument with a lower index than required positional argument. Okay, the problem, positional argument ordering. So I understand why this happened because initially the reason why I was testing this out was because my question was if I have if the required arguments are, read first and then the optional arguments are read next, that means that all of the required arguments would have to be put at the beginning, right? Now, what happens if I have them in like a different order in the struct itself? So what if I do required, non-required, and then required? Like what's going to happen there? I guess I got the answer. It kind of panics. Um, okay. All right. Okay. Gemini is explaining this. In your CLI struct, you have three positional arguments defined without arg short or arg long. Clap evaluates them in the order they are defined from top to bottom. Okay, required, optional, required. Think about this from the perspective of the CLI parser when a user runs your program. If they type hello and world as two separate arguments, does hello go to say something and world go to name? If so, arg02 is missing, causing a runtime error. Or does hello go to say something and world skips name to fill the required arg02? Because CLI parses read arguments left to right. No, because CLI parsers read arguments left to right, you cannot put an optional positional argument before a required positional argument. All right, okay, right. I'm confused. Wait, okay, that makes sense. I'm also confused as to why it's saying index 2 for name. Clap uses one-based indexing for positional arguments. Okay, that's all I was looking for. That answers my question. Great. So now that we have that taken care of, give me a second. Okay. All right. Um, moving on, let's go to that conversation that we were having. Where is the conversation gone? Okay, I was talking about oh, I think, yeah, here it is. Okay, so we were looking into, there were a couple of things that I wanted to explore here that I didn't really look into after the stream because I kind of just forgot about it. Command is one of them. I was supposed to look into what exactly command does because what Gemini has told me so far is that this pulls metadata, um, like the version and description of your app, straight from straight from your cargo.toml file. Okay, okay. I feel like that's not enough. That's not satisfactory information for me. Um, yeah, I need to look deeper into this. I'll look deeper into it. After we have gone through these other options. So we were looking into positional arguments, and from there we had gone to um, name, and that's when I got the idea to do, you know, uh, a required argument because we already had a non-required argument. Sorry, zoned out. Okay. Inside the struct, each field represents a different flag, option, or positional argument. The positional argument is name, option string. Because this field doesn't have an arg attribute specifying a flag, so arg attributes specifying the flag. Okay, if we are looking at config, what let's oh, does it say file? Yeah, it does. Config file. At the bottom, um, value name, file, and then there's short and there's long. I need to look into what the short and long thing is as well. But for now, carrying on with this, attribute specifying a flag, clap treats it as a positional argument. Wrapping it in option means it's optional. If the user doesn't provide it, it will simply be none. Okay. The config file option. Short automatically creates a short flag. Oh, that's what it means. Short and long flags. Okay. Now I get it. I did not understand that. I didn't immediately like guess that that's what it was. So if I remove short, does it just stop showing up? It does. Okay. That is so interesting. Okay. I mean, that's not really something I'm interested by it. That is so interesting to me. Okay. Automatically creates a long flag using the full field name. Short automatically creates a short flag using the first letter of the field name. Value name, when someone runs help, it will look like config file instead of config, making it more user friendly. So let's try removing this and see what shows up. Okay, all right, now I get it. So we can add in a bit of extra info in here to let people know that, oh, this is expecting a file. So they'll then give a file path, file name, whatever. Okay, then we have the debug counter flag. In this, we have action. This is a cool feature for verbosity. Every time the user passes, actually, yeah, that's great because I believe I'd seen this. I'm pretty sure it's a thing in multiple CLI applications, but right off the bat, or off the top of my head, what I can remember is in Radari, you had this kind of thing. Actually, in a couple of others as well. In Radari, you had this where you could specify like multiple of some alphabet, I don't remember which one, to change the level of analysis of the binary that's going to happen. Um, I think in some debugging tool, or maybe it was within Radari itself, one of the, I think, commands that you could give, that would be like the number of the same alphabet that you would give, that would dictate the amount of verbosity of the output. So it could be very concise, brief and concise. It could be slightly detailed. It could be kind of detailed. It could be incredibly detailed. So this is one such situation where we can create like multiple levels of something. Okay, every time the user passes the flag, it increments the number. All right, if they run your app with 1D, debug will be 1. If they run it with, and okay, that is why we were able to use match over here. And also, that is also why debug is an unsigned byte. Okay, okay. Since it's a U8 and not an option, it defaults to 0 if not passed. Okay, then the subcommand structure. This is how clap handles nesting commands like git commit or cargo build. Okay. This tells clap that the user might type a subcommand next, and it should look it should look at the command's enum to figure out what's valid. Okay, so let's take a look at the command's enum. Within the command's enum, we have test, and here we are able to give some more commands as well. All right, okay, okay. That's great. That's actually, holy shit. And this is clever because in Rust, enums can have different types of variants. You can have like a single value, you can have a unit variant, you can have a struct variant. I think there were one or two other types of variants that I can't remember. But yeah, you can have multiple different types of variants all within the same enum. So there's different types of information that you can pass into one enum. Okay, this tells clap that the user might type a subcommand next, and it should look at the command's enum to figure out what's valid. Then in the subcommand, oh yeah, okay, yeah, I just realized this. We have this thing. Can we do something like, wait, yeah, what do we do when test is called? We match command? Okay, hold up. That comes under command because command is a field in the CLI struct. Okay, all right. So then I could add more commands. I'm guessing we could add like sub commands maybe. Is that a thing, or does the level of um what do we call that? The I'm not able to think of the right word, but like that thing where you have a command, the command can have a subcommand, the subcommand can have its own subcommands, like that level branching, I guess. I'm not sure. Um, but yeah, I haven't tested that out. I'm kind of curious about how that would work. We could try something here. What if I created another subcommand? Let's do derive subcommand enum commands. No, no. This is supposed to be subcommands. Oh, that's going to cause a problem. Um, for now, for the sake of simplicity, let's say commands o2, and in here we're going to create I don't know, some cmd o1. Okay, and this is expecting. Well, okay, yeah, this doesn't have to. This is a command, isn't it? This is a command, so I have to give it something. So let's say some cmd o1. Um, can it just be an empty struct? Is that okay? I think that's okay. All right. Then we can do command. This is also called command, right? Let's I don't know. Let's say sub cmd commands o2. Okay, we have an issue here. Consider annotating so and so for clone. Doesn't satisfy 8 bounds. What do they do over here? Command, subcommand. Okay, I'm missing this thing. Let's yank this and paste it here and see if that solves the problem. It did. Okay, great. So I'm guessing this macro, it does a bunch of code generation for us. We still seem to have an error. Oh yeah, the error is that I haven't handled all the command could be this. It could also be some because I made it an option, right? Actually, no, no, no. Wait, it's not. The issue is not here. The issue is not here. Sorry, give me a second. Okay, there we go. Um, missing structure fields. Oh, it's because I added a subcommand there. Um, I don't remember how we are supposed to specify this pattern. Yeah, I know it's. Oh, can I just do? Yeah, yeah. I was wondering if I could just do that. Let's try that. Rename to so and so. Yeah, let's ignore it. Okay, but then in here, yeah, this gets a little bit complicated. I'm overcomplicating this for nothing. It's not like I'm gonna have a subcommand for a subcommand, but I just want to like test it out. I want to see what I'm able to make out of it. There's only one command that can be entered, right? It's called sum command o1. Let's just yeah, let's just do this. We'll do sum commands um test list would be this, and this would be, what is it called? Commands O2 some command. And I think we are good. No, I think we might have an issue here. What's the issue? Oh, expected so and so. I made a mistake somewhere. That's the mistake. Hold on. I need to. What was it? Something snippets? What was the what was the plugin called? Because I'm having this issue where the key binding for turning this thing off. Hold on. Um, NeoVim snippets. NeoVim LazyVim snippets. Sorry about that. Um, oh, mini snippets. Okay, should be under mini snippets then. Um, Probably not. Let me open up the GitHub repo because they have some of the commands mentioned there. Give me a second, I'm just opening this thing up. So we have mini snippets. Under mini snippets, we have wait, was it mini snippets or something else that I was using? Um, okay. All right. Where is the thing to, because I wouldn't be having this issue on this machine. Actually, I could, wait, that's odd. That is really odd. Hold on. I just remembered that I can search through here. Snippet. Session stop is Control C, and that is what's not working. What if I do this? That's not working either. Um, Snippets. Command mini snippets dot session dot stop. Yeah, the issue I'm having is wait, C is supposed to be control, isn't it? I think so. I think C is supposed to be control. What if I look this up? Right, so we have this and this. This is the issue that we are running into here. Um, I could go into what is Control Z for something? Let me just confirm that Control Z is for nothing. Okay. Control Z is for nothing. So I think what I'll do is go into um, the config file for, where was it? Slime. It's Control C. We'll change that to Z and close. Yeah, let's save that. Reopen this, restore, and we should hopefully be good. Give this a second to load. Okay, Control Z does that now, and Control C. Okay, okay. Let's look at that. Wait, that's interesting. So what is uh backup? Something is um odd here. Sorry, give me a second. I had a little bit of a issue within NeoVim that I need to fix. Let's create this, I guess. Yeah, let's do that and that. I need to. All right, there. That didn't create it. You know what? I'll rewrite the entire thing. But no, I'm confused as to why snippet does snippets need to start? Maybe snippets needs to start. Okay, let's do that. And then in here we're supposed to do commands, test, there's snippets, and I can shut it down. Okay. So now that I know it's working, yeah, snippets just hadn't started up. Wait, does that mean now I'll find it? Uh, I'm still not finding the thing that I'm supposed to find. I mean, I'm seeing many snippets, but the specific shortcut that I'm looking for is just not there for some reason. Mini snippets. It's just this. Why is that? Okay, what if I change this? And then we come back here, close this, reopen, do this, let that load up. Snippets hasn't loaded up yet, has it? It hasn't. So we're still doing the Vim snippets. Hold on. Wait, where am I? I'm supposed to be in here. Okay, so let's rewrite this entire thing. Okay, sum, and then in here we have commands, test. Actually, for the sake of getting the snippets thing, uh, we don't have anything for that. For this though, we definitely have commands o2 dot subcommand, and we can leave a trailing comma, and then here We don't need anything there. I like that when I close that, it goes to the next snippets thing. Yeah. Okay. And now we are good. So now snippet. I'm I'm confused as to why it's not showing the mini snippets shortcut now. Previously it was showing it. I mean, on the bright side, now it's working, but yeah, I'm kind of confused about that. It's working now, so I mean, I'm not gonna complain. Um, yeah, yeah. Now in here, what I want to do is just have a print line saying, I don't know, some CMD01 called, and let's compile this and see what it even looks like. First, let's look at help. No value can reach this. Wait, why is that? This one matches all relevant values, and so nothing reaches here. So how do I thought I thought the underscore was supposed to be to, like, I thought it was supposed to be to ignore the value of this. How is it that we will never... Okay, okay, let's make it an option then. Okay, instead of command, we will say option this. Okay, so now here we get an error. Here we can say none. That should work. And then here we add in some, I guess. There's an error. Um, expected comma, expected indent. Oh, is it this? Oh, it was this. Okay. Now let's see. We don't have that issue anymore. I'm also noticing that, okay, what if I did test help? Does that work? Yes. Okay, holy shit. It handles multiple levels. So for test help, it created a subcommand for us, some CMD01. So if I call some CMD01, oh, it's because we have a positional thing. So um, I meant to write ABC, but okay. Some CMD01 called. Okay, all right. So now we know that it's not just commands within it, it's also subcommands within those commands that were, or rather, it's not just subcommands within it, it's also sub-subcommands that work. I need to study match a lot more because this is telling me that I don't fully understand pattern matching in Rust, specifically when it comes to, like, items that involve multiple fields. I need to go back and read that entire match thing again. I feel like I don't fully understand it. Um okay. Right. Okay, we can move on from this and go back to this thing. All right, so test. Actually, first we look at the macro subcommand. This turns this enum into a collection of subcommands. Test, this defines a subcommand named test. Clap automatically converts camel case to lowercase for the CLI. Inside test, you have a list flag. Because it's a bool, it acts as a simple toggle switch. If they pass hyphen L or hyphen, okay, hyphen L or hyphen list, it's true. That's interesting. Wait, okay, okay, wait, so if we want to check, but no, I don't get, hold on. Test L. So if I pass, oh, it's not for test, it's for the argument itself. So something I could do here is I could specify, I don't want to type all this again. Let's paste that, do that, and get rid of that. There. Okay. Um, let's say some bool. That's too long. Let's say SB. SB01 is a Boolean. And then all I would need to do is pass that thing as, just pass the flag itself rather than some value. So I could check here if reference the CLI SB01, then print line SB01 flag passed. Mismatched type expected bool found so and so. Okay, so here I need to worry about moving. I need to ask Gemini. Um, because what it's saying is do this, right? But then I'm concerned about like what happens over here, what happens with CLI, because SB01 is a Boolean, so I'm assuming it's just gonna copy. It's not like um it's not gonna move the value, it's just gonna copy it. If it needs to copy, it's gonna copy. Is there really gonna be a copy or a move here, or does it like implicitly just reference it or something? Hold on. Hey, I have a struct, um, my struct O1, uh, within which I have a bool SB01. In main, when I try doing if, well, my struct O1 so and so, so and so, in main, um, after creating an instance of my struct O1 called MS01 or okay, yeah, whatever, MS01, when I try doing if ampersand MS01 dot SB01, I get an error. An error saying bool was expected, but ampersand bool was provided. I don't understand. Shouldn't I use a reference to MSO1 since it might move? To be fair, it's not the moving. Actually, oh God, hold on. I asked the wrong question. It's not going to move. It's the value that could move. It's the value that could move. I need to rephrase this question. No, no, no. Because I approached it with the wrong understanding. Um, shouldn't I? No, let me say I don't understand. I usually, if it's a value that can actually be moved to prevent it from moving, we use a ref. And if we do that with a copy with a value that can be copied, um, it just copies. What's going on here? Okay, it's super common to run into this when you're used to how Rust handles, when you're getting used to how Rust handles types and conditionals. Here's exactly what is happening. Rust does not automatically truthy test. What is truthy test? Truthy test. Um, right, I can look into that later on. Rust does not automatically truthy test references. An if condition in Rust strictly requires an expression that evaluates exactly to the primitive bool type. When you write ampersand mso1.sbo1, you aren't providing a boolean, you're providing a pointer to the boolean. Let's break down why your intuition about moving slash copying is totally right, but why it doesn't apply to the if statement the way you think. The type mismatch. When you use the ampersand operator, you're explicitly creating a reference. Okay. Where was I? Yeah. You are explicitly creating a reference. So ampersand mso1.sbo1 is an is a reference to a boolean, but mso1.sbo1 is just a boolean. Rust's if statement does not do implicit coercion. I think that's where we run into an issue here. It's the concept of coercion. Yeah, yeah. Sorry, zoned out. Okay. It Rust's if statement doesn't do implicit coercion, like turning a pointer into its underlying value, just because it knows a boolean is inside. It sees an ampersand bool, throws its hands up and says, hey, I need a bool, not a reference to one. Copy versus move in this context. You are 100% correct about your ownership rules. Hold on. If a type implements copy, like bool does, accessing it or passing it around copies the value rather than moving it. Therefore, you don't actually have to borrow it to prevent a move. Because bool is a copy type, simply reading so and so leaves the original struct completely intact and unharmed. No ownership is lost. Okay, so to fix it, you have two options. One is to just drop the ampersand. Since bool implements copy, it just reads the value directly. Um, it will implicitly copy the Boolean without moving anything out of MSO1. Sorry, zoned out. Okay, option B, dereference it explicitly. If you must pass a reference around for some other reason, or if you just want to see how to make the reference work, you have to explicitly dereference it using the asterisk operator to get the underlying bool. Summary, you don't need to. Okay, all right. You know what? That's good enough for me. We are gonna, yeah, okay. So let's pass, I forgot what it was called, just S? Yeah, SBO1 flag passed. So, okay, cool. Good to know. Good to know. All right, holy shit, dude. Exploring even this simple example that the the crate documentation gave us, that alone has been it's taught it's like explored a whole bunch of different things. Um, there's optional arguments, and from optional arguments, from optional arguments, I got the idea to do, required arguments. Zaynar, hello, hello. How's it going? Um, I'm okay. I'm okay. I'm currently learning some Rust. Specifically, we are exploring the clap crate, which is used for parsing command line arguments. This crate makes it easier to accept command line arguments and do all sorts of processing with it. At some point later, once I'm comfortable with clap, I wanna kind of bridge the knowledge that I gained from the Inquire crate and the knowledge that I gained from the Clap crate. And then there's a knowledge base application that I'm building in which I'm actually going to be using both of them. The Inquire crate is for giving the user prompts within the CLI application itself, and it provides you with various tools for like validation and stuff. Low level evil, I'm Python maxing. Good idea to build something with what you learn. True. Yeah, yeah. Actually, speaking of that, I started doing this thing where I because I have this philosophy that if you are learning a new programming language, just build things with it. even if it's dumb things, even if it's stupid things, just build things with it. Because the more projects you work on in a language, the more experience you'll gain, the more things you learn about the language. And that's why there is one silly application that I'm working on as well. There's actually going to be a bunch that I'm going to work on. I'm going to create like a repo to store all of them. Fortunately, um, within Rust, specifically using cargo, you have the option to build multiple examples within the exact same project. So this way you can do something like, hold on, do I have that set up here? I don't remember. What's the structure that I've set up here? Bin. Well, okay, this is one good example. So you have the concept of binaries and examples in Rust, specifically in Cargo. So what you can do is you can have multiple different types of programs. One program could be this clap bin, and that takes in like command line arguments and parses them and stuff like that. Another binary could be this one, which for now let's make this have, yeah, this is just going to print something out. So if I try to use this, if I do sum01, now this binary is doing some, now this doing cargo bin over here does something else because I'm able to specify a different binary. Similar to this, there's a concept of examples where you can create an examples directory outside of the source directory, but still within the root of the project. And then, similar to how I'm doing cargo run bin, you can instead do example and then type whatever name of the example and run it. And it's all still going to be within the same project. It's all of those files. They're gonna share the same dependencies. Um, and yeah, that's like incredibly convenient. Okay, now, um, by the way, you said you're Python maxing. What are you working on today? Where where was I? Test defines so and so. Yeah, okay, I was reading this. Test defines a subcommand named test. And then inside test you have a list. Yeah, so we covered that. We are doing that. That's gonna be a Boolean, and this is a way to just not accept a value or not need to accept a value. So I can use that as well for like conditional things. Today I'm working on some work projects while exploring local AI. Hell yeah. Hell yeah. I think further from this point, I'm pretty much done with clap. Like I've kind of understood. I need to explore pattern matching more because I've done pattern matching with match, but now I feel like I don't fully understand. Not a big fan of relying on cloud API AI. I feel that. Yeah, I feel that. Definitely, if given the option, I would like to host a bunch of the different language models that I work with. Um, I mean, there are, pros and cons because they do tend to be more on the heavy side. You can get much more lightweight models. You can get like quantized models and stuff, but they have their pros and cons. But yeah, I would definitely like to host my own. Working on extracting and transforming point cloud data. Um, from LiDAR scans taken on a plane. That is interesting. Wait, working on extracting and transforming cloud data, point cloud data from LiDAR scans taken on a plane. Sorry, zoned out. Okay. I'm working with the smallest stuff as it's all my old gaming PC can run, running Q4 Quen 3.6. It takes time to understand how to set it up properly and optimize for performance, but it's impressively good, considering only 8 GB of VRAM. One of my problems is a lot of the stuff that I'm running, even if it does have a GPU, it's not going to be the best GPU. And it's not even a GPU from like within the past 5 years. So I I have to see to what extent I'm going to be able to benefit from that. I can to a certain degree. I wanna try and load a bunch of these models using Hugging Face transformers, and transformers does give you options um, to kind of offload the running onto the GPU. By default, it's not going to be running on the GPU. I did look into Quen as well. In fact, I think somebody had made a quantized version of Quen. I can't remember if I'd seen one or not. I believe someone did make a quantized version of it, so you would be able to run it on smaller, on lower, on more memory constrained machines, let's say. I'm running llama.cpp for local inference. Quen 3.6 has very many quantizations. I actually haven't touched llama CPP. I'd been meaning to look into both llama CPP and ollama, but I didn't get around to doing either of those. I kind of want to finish with HF transformers, and through that, I want to be able to, because I think to a certain extent, both Llama CPP and Ollama would allow you to even offload the calculations to the GPU. I don't know how you go about setting that up, but I'm trying to set that up in transformers. I know that you can do it. It's just not something that's like default behavior. So they have a separate library that you would have to use along with transformers. I'm working with RTX 30 series, 8 GB VRAM, and 32 GB of DDR4. Cheap and cheerful, but good enough for what I'm doing. Yeah, you need to do a fair bit of research on how to run the models well. Yeah, I don't have, like, I think my collective hardware, I have 4 machines running right now, and all of them total, I don't think even that comes up to 32 GB of RAM. Um, And in terms of GPU, it's all 5+ years old GPUs. One is a NVIDIA MX 110. Another one is it's an AMD GPU, but it's on a probably decade old laptop. And both of these are laptops. The MX 110 GPU is also on a laptop. So I'm not sure how well these would perform, but like even keeping GPUs aside, I would still like to learn how to host them myself. Not necessarily using something like Llama CPP or Ollama, as great as they may be. I want to try and set up the architecture myself. That's just something that I wanna try as a challenge for myself. At some point later, though, I will look into either one or both, maybe. Llama CPP and Olama. Um, these are, from what I understand, they have their, like, they're both binaries, right? I mean, you would be running the program, and I think they also have their Olama, at least has its own like GUI. Does it also have TUI? I don't remember. Hold on. Let me look this up. Um, hold on. Hey, do llama.cpp and Olama have GUIs, or are they CLIs? Olama is just a wrapper of Llama CPP, easier to work with if you don't want to compile Llama CPP and deal with more complicated args. Okay. By default, both llama.cpp and Olama are CLIs, but the open source community has built incredible GUIs for both of them. Olama runs as a background service, a daemon, with a CLI. You type commands like Olama run so and so in your terminal to download and chat with models. Popular GUIs for Olama. Wait, if it's a CLI, how is the chat thing being implemented? Okay, Llama is a CLI only for loading and launching models. You can have a front end if you want. I just have a bunch of batch files to run my setup. So in my case, I'm gonna have to uh, try running this in Docker, because I'd imagine there's a couple of like dependencies and stuff that you might need if this is a binary that I have to install. Is that a thing? Hold on. When I install llama.cpp or olama, um, can I use Docker? Because I know in situations where a project is fairly complex, and in order to run it, you need a bunch of dependencies. They will give you an option to run it in Docker instead of having you install all of the dependencies, globally on your machine. Okay, yes, absolutely. Both Llama CPP and Olama have official, highly optimized Docker images available. Using Docker is a popular approach because it packages all the messy C++ dependencies, build tools, and hardware libraries for you. You can run it in Docker. I just install it normally with CMake. I would I would usually go for that. I would usually go that route, and as in the installation route. But then a couple months ago, when I learned about Docker, I realized that when I'm installing more complex applications, or even like building them, from source, there is a chance that there might be a need for dependencies that could somehow conflict with what I've got on my machine, or it could cause some other issues. And just to avoid possible issues, it's not like a sure thing that you will absolutely run into issues, but just to avoid possible issues in the future, I would prefer to run it in Docker. I should also look into how, like, would that stand in the way of GPU acceleration? I don't think it would, because a lot of people are even using, what is that called? OpenClaw through Docker. Docker is an extra overhead on the system. I'm running on the exact edge of what the PC is capable of. Docker is much better for containerized deployment. No, you can configure a Docker container to pass through GPU. Okay, that's good. That's good. So then, I guess in that case, I should be looking into, because okay, you know what? That brings me to my next question. Wait, I'm going to ask this question. Um, hey, so I want to be able to run, yeah, I want to be able to run LLMs locally, and I want to build the not architecture, but the program that's going to be used to chat with them myself. I want to use something like HF transformers to load and run the models. But if you don't have hardware to support things, it's difficult. GPUs are so expensive at the moment. True. For me, my issue is not just that GPUs are expensive, it's the fact that I barely even have a machine in which I can install the GPU. Um, so like if I am running anything, like right now, GPUs are just out of the question for me. I have four machines. Um, One of them is, so I have four machines. Two are laptops. One laptop is, let's say, 6 years old. Another laptop is a decade old. Then I have two desktops. One desktop is maybe 12 years old or 14 years old or something. And the other desktop is close to 20 years old. The oldest desktop that I have is running maybe 2 GB of DDR2 RAM. Like that's how old my a lot of my machines are. The other machines they're running probably DDR3 or 4, one of these two. They're either running DDR3 or 4. I think it might be 4, but it might also be 3. So that's how old these machines are. And um, the newer GPUs, I doubt they're even gonna like fit in these. There's also another issue. There's only one desktop in which I can actually install the GPU, and I'm not too comfortable with installing the GPU into that desktop because of, well, there's certain reasons. And I can't install the GPU onto the two laptops. So either way, GPUs are like out of the question for me unless I want to go and buy, another PC. Um, like at that point, I would much rather just like rent out rent out cloud hardware for doing my processing stuff. But before I do any of that, I want to I want to get the knowledge of setting up my own local infrastructure for running these models. Currently, I am not going to be my hardware is not going to be able to run a bunch of these different models. Maybe the heavily quantized version of Quen I might be able to run. I'll have to look into that. But that's also going to be CPU. Actually, one of my machines here, the laptop with the MX10 GPU, I could see if things work out because I managed to get the GPU working even on Linux. And I mean, honestly, that wasn't even really a challenge. Gemini just gave me the specific commands I needed to install the GPU and also maintain it. And since then, it's been working fine. So I'm even able to like play games on it on the rare occasion that I do play games. Oh, I was asking this question. I want to use something like HF transformers to load and run the models. I know that Llama, I forgot what my question was supposed to be. Llama CPP and OLlama exist, and they allow you to download and use the models. I don't know too much about either of them. I'm wondering what would the difference be between what I'm making and what they are able to do. Are there specific optimizations that they are applying somehow? Actually, okay, this brings up another question. Applying somehow. Also, where are they pulling the models from? Sorry, zoned out. Also, where are they pulling the models from? Are they doing something like HF transformers, where the model architecture is implemented in the library while the is implemented in the library while the is implemented in the library and then um, the safe tensors, guff, etc. files provide different configs to run the models in. Different configs and weights to run the model in. Okay, it's awesome that you're building your own local LLM chat inference from scratch. Doing this with Hugging Face transformers is the perfect way to truly understand what's happening under the hood. Uh, to answer your question, your custom Python app and tools like Llama CPP or Olama are trying to achieve the same goal, which is running an LLM locally, but they take radically different technical paths. Here's exactly how they stack up against each other. Where do they pull the models from? Your Hugging Face app pulls it directly from the Hugging Face hub. It downloads the standard model repositories containing configuration JSONs, tokenizers, and weights, typically in safe tensors or bin formats. Llama CPP, historically, you had to download models manually or convert them yourself. Today, it natively supports downloading guff files directly from the Hugging Face repos using the Hugging Face Hub API. What AI are you asking? It's very sycophantic. I'm talking to Gemini. Hold on. Where was I? Yeah, so that's Llama CPP. Olama. Olama runs its own curated registry, essentially a model library hosted by Olama. When you run Olama run so and so, it pulls a bundled model file and guff weights from its own servers. Though behind the scenes, those models are often imported and packaged from Hugging Face. That's what my next question was going to be. That, like, okay, how are they getting the models? And it turns out that yeah, they're most likely also pulling it from Hugging Face. Okay, then architecture, code versus a guff format. You asked an excellent question about whether the architecture is hard coded into the library. With Hugging Face transformers, yes. Hugging Face works exactly as you described. The library has explicit Python files defining the math and neural network architectures for every model. And then the weights just fill in the numerical matrices. The catch here, if a brand new model architecture drops tomorrow with a wacky new attention mechanism, you usually have to wait for Hugging Face to write the Python code for it or use trust remote code equals true to download the author's raw Python scripts. Then Llama CPP and Olama are Llama CPP revolutionized this. It uses a single file format called GUF, which is GPT generated unified format. GUF files are unique because they are self-contained. They contain the model weights and all the metadata required to run the model, such as the architecture type, the number of layers, attention heads, and even the tokenizer vocabulary. While Llama CPP still needs C++ code to know how exactly a Llama layer versus a Gamma layer to what how to oh my god, holy shit, wait, let me read that again. While Llama CPP still needs C++ code to know how to execute a Llama layer versus a Gamma layer or Gemma layer, um, the GUF format allows it to be incredibly flexible and backwards compatible without needing separate configuration files. Wait, back up. It still needs C++ code to know exactly how to execute a Llama layer versus a Gemma layer. The GUF format allows it to be incredibly flexible and backwards compatible without needing separate configuration files. Note, Olama is essentially a sleek, user-friendly wrapper built on top of Llama CPP. Okay, that's what you said earlier, Zenar. So it inherits all of this. What optimizations are they applying? If you write a standard Hugging Face script in Python, it will likely run much slower and consume vastly more VRAM/RAM than Olama or Llama CPP. C++ plus Python overhead. Llama CPP is written in pure high-performance C, C++. It avoids Python's interpreter overhead and memory management issues. Then advanced quantization. While Hugging Face supports quantization via libraries like Bits and Bytes, Llama CPP was built from the ground up for GUF quantization. K-quants like so and so, so and so, so and so. They can compress a 16-bit float model down to 4 bits with almost zero loss in conversational quality. Then unified RAM versus VRAM offloading. If you try to load a model in Hugging Face that is too big for your graphics card, uh, that is too big for your graphics card, it will either crash with an out of memory error, or you have to manually configure complex device mapping, which severely slows things down. Llama CPP and Olama excel at layer offloading. If your model, hold on, this makes me wonder if there are Rust bindings for Llama. So llama.cpp Rust. Because on the Rust side, we have Candle. I can look into Candle. I have looked into Candle. So what I'm getting here is that if I want to run this in an optimized way using HF transformers and Python, I'm not going to accomplish that. I can use that for prototyping, but when I'm actually running the thing, I probably want to run it using something like Rust or C++. Um, I would much rather build my own sort of thing for, a chat interface, though that becomes a lot of unnecessary work. That being said, if I am hosting it locally, then I mean, I don't mind doing that bit of extra work. Um, I should also look into if there are more standardized methods, if there are more standardized methods of doing this. like building an application, let's say in Rust, where a bunch of the tools are already provided to handle the LLM's response. Okay, so there is a crate called Llama CPP Rust. Um, Let me open up the GitHub for it. Is it actively being maintained? Let me look at that as well. Oh, yes, it is actively being maintained. It is like, it has commits from like 3 hours ago. This is the home for Llama CPP2. It also contains Llama CPP sys bindings, which are updated semi-regularly and in sync with Llama CPP2. Is this, so is this Llama CPP R, wait, this project was created with an explicit goal of staying as up to date as possible with Llama CPP. As a result, it is dead simple, very close to raw bindings, and does not follow semver meaningfully. Oh, as in semantic versioning. Check out docs.rs for crate documentation or the README. You know what? Let me open this thing up here. Um, Hold on. I'll open the thing up over here, and then we can read the entire thing here. Okay, so we're going to do first Llama CPP. We're going to open that up. Oh shit, we are dropping frames. Or were dropping frames for a little bit. Give me a second. I'm just loading the stuff. Okay. Llama CPP, then Llama CPP Rust, and then from there I'll open up the other thing. I was also, okay, I might as well open up Candle as well, right? There's Candle and there's Burn, but with Burn it's more for like building your own models or translating other models into something that Burn can run. Um, Candle has a bunch of the different architectures, I believe, including Llama implemented. So we're going to check out all of these. Let me also, okay, all right. So this is Llama C, C please, what? Llama C++. Um, and then here we have Llama C++ Rust or CPP Rust. Okay, earlier I was saying they have commits from 3 hours ago. They're actively working on this. This is from like three minutes ago now. Um, Hold on. Yeah, okay. So they mentioned that there's a docs.rs thing. So let's take a look at what the API is like, or look at the README for high-level information. Is the README long, or is the README elsewhere? This is the entire README, right? Or do they have the README somewhere else? This is the entire README. Okay, all right. Okay, bindings for the Llama CPP library. As Llama CPP is a very fast moving target, this crate does not attempt to create a stable API for all the Rust idioms. Instead, it provides safe wrappers around nearly direct bindings to the Llama CPP, nearly direct bindings to Llama CPP. This makes it easier to keep up with the changes in Llama CPP. but does mean that the API is not as nice as it could be. Okay, so they have examples here. Let's look at a simple example. Llama CPP is extremely active, as are the forks around it. I update it every hour. That's wild. Okay, there's an example here. Um, I wasn't expecting it to jump into GitHub. I was expecting it to give examples like directly in the docs page, but I guess it's not doing that, which is fine. I mean, looking at it on GitHub isn't really a problem. Let me collapse this and let's see. Okay, this is a translation of a simple of simple CPP in Llama CPP using Llama CPP 2. Oh, wait. This is for implementing the model architecture, isn't it? Yeah, I think is it? Wait, no. Hold on. Hold on. Okay, Llama CPP is words. Oh my God. Llama CPP is a highly optimized C++ library designed for maximum performance on local hardware. At its core, it is purely a CLI tool. You run it by passing complex arguments into the terminal, examples specifying threads, batch sizes, and prompt formats. It has built-in third-party GUIs for no, there are built-in third-party GUIs for Llama CPP. LM Studio is one of them. Okay, under the hood, the popular GUI apps like LM Studio and Anything LLM use Llama CPP as their core engine. They wrap, you know what? Okay, often a random update will give you super beneficial changes. You know what? In this situation, I can imagine that being a thing because uh, there have been like various like there was this one there was this one this was a while back and this was in Llama CPP specifically where they had realized how to load big models, but like I think it was something about loading them in chunks, and they figured out how to do that, and then that somehow became a meme online. People were joking that they learned how to use mmap or something. I don't know, it was something along those lines. So I can see that being a thing. Something new that gets implemented could be, and especially if you're running like newer GPUs, because your what did you say, RTX 30 series, even though we are now in like the 50 series or 60 series, I think 30 series is not that old. So like there's a bunch of stuff that your hardware would still be able to benefit from. I'd imagine probably even stuff that maybe even your CPU would be able to benefit from, because there would be a certain amount of stuff going on the CPU side as well. Okay, there's a built-in server. Llama CPP comes with an executable called Llama Server. When you run it, it hosts a local web address. If you open that address in your browser, it provides a functional built-in lightweight web GUI for chatting and testing parameters. You know what? After reading all this, I am kind of interested in trying this out. That okay, this has me wondering, hold on. Hey, so what exactly is going on in Llama CPP? Have the architectures been implemented? init, implemented, implemented init, or are no, implemented init, and then guf files are basically providing different settings, because that's usually how it's supposed to go, right? I mean, the architecture itself, Quen is also an architecture. Llama is also an architecture. Um, there are a couple of others that I can't remember the names of right now. Microsoft had a famous one as well. Generally, generally the architectures would get implemented, and just the architecture is not enough. With neural networks, you have the architecture, and then you have the settings for that architecture. You have the weights, and you have the configuration for the architecture. Um, yeah, are basically providing different settings and weights to run the model with, or is something else going on? Okay, that is exactly what's happening under the hood, but with one massive twist that makes Llama CPP so incredibly fast. Um, okay, the Llama CPP code base is where the architectures are explicitly hard-coded and implemented. Because Llama CPP is written in pure C, C++, it cannot dynamically figure out a brand new model, a brand new model math architecture or math structure, a brand new model math structure on the fly like Python's PyTorch can. Instead, the developers manually code the exact mathematical structures, the compute graphs, for popular model families like Llama, Minstrel, Gemma, Phi, Quen, and DeepSeek. When you run Llama CPP, it uses GGML, its underlying tensor math library, to build a lightning fast execution plan customized for your specific hardware. Um, it checks if you have an Apple silicon chip using Metal or NVIDIA GPU using CUDA, and prepares the exact assembly level code to run those matrix multiplications. All right. Then you have the file, the self-contained container. If Llama CPP is a factory, the guf file is the exact blueprint package and raw material shipped to it. Okay, I kind of get that. Okay. A guf file is a single unified binary file that contains three main things. Sorry, got distracted. Contains three main things: the metadata, um, which is wait, okay, the metadata, the hyperparameters, and the weights. So the metadata explicitly tells Llama CPP which architecture it uses. For example, it will contain key value pair. It'll contain a key value pair like general.architecture equals Llama. When Llama CPP reads this, it says, okay, I need to spin up my own Llama execution graph. Then you have the hyperparameters. This includes the specific configuration numbers for the exact model size, such as the number of attention heads, the embedding dimensions, the context length, and even the exact tokenizer rules, which is how text is chopped into numbers. Then you have the weights. You don't need to understand all of it to make it work. Local model info is extremely complicated. You're right. You're right about that. A lot of these tools have been made so that it becomes a lot easier for people to just run the models by plugging things in. In my case specifically, because I'm going to be going deeper into deep learning, that's why I kind of want to understand how all of this stuff works. That's why stuff like hyperparameters and weights and stuff makes sense to me, because I've so far I'm still very early in my deep learning journey. I've so far only covered feed forward neural networks, but I also want to learn convolutional neural networks, recurrent neural networks, and then transformer based neural networks, which most of these models are actually transformer based neural networks. That's why you see, or at least that's what I know, um, is that they are all transformer based neural networks. That's why you often see this thing about attention heads in there. Where was I? Exact model size, such as attention head, so and so, so and so, so and so. Okay. Then you have the weights. The actual trained brain cells of the AI, usually heavily quantized, so they can fit into the computer's RAM or VRAM. The magic twist is zero copy memory mapping. Because of how the GUF format was designed, Llama CPP doesn't actually read the weights into RAM the way normal software opens a file. Instead, it uses a trick called mmap. Inside the GUF file, wait, instead it uses a trick called mmap. It aligns the data inside the GUF file perfectly with your computer's memory boundaries. When you launch a model, Llama CPP instantly points your CPU or GPU directly at the file on your hard drive. Why this matters? It means a 10 GB model loads in less than a second, uses almost zero extra RAM for the loading process itself, and can safely swap pieces of the model in and out of your system cache on demand. Okay, okay. All right, so this has me wondering something. If I use Llama CPPRS, which are Rust bindings for, oh, actually, wait, um, is llama.cpp also a library and not just a binary? If so, what are the possibilities with it in terms of using, in terms of loading and using a model rather than just building model architectures or arches. Also, if I use Llama CPP RS, which provides Rust bindings for Llama CPP, um, what all would I be able to do with it? Because here's the thing, right? If it's providing bindings, that means Llama CPP has a library as well. It's not providing bindings to a binary. It probably would have said that. It says that it's providing a safe wrapper. A safe wrapper would be, a wrapper around a function. Um, Okay, this enables CUDA GPU support, and then sampler adds so-and-so struct for a more rusty way of sampling. So I'm probably not going to be using the CUDA thing for the time being. It's going to be strictly CPU. At some point later, good to know that there's going to be CUDA support. Also, um, Candle, Candle. I need to look at. Oh, this is a wrapper around the Llama C++ library for Rust. Back up. This is. Hold on. So wait, what am I looking at here? This is the home for Llama. Oh, okay, okay, all right. So they have both the crates here, right? They have Llama CPP and Llama CPP sys. Okay, okay. Hold up. Let's look at Candle. Candle is a minimalist ML framework for Rust with a focus on performance, including GPU support and ease of use. Try our online demos for so and so. Um, they have a bunch of these architectures implemented. So I'm assuming we can use them out of the box in Candle. Yeah, yeah, I think so. Um, okay, okay. Optimizers, a collection of optimizers including SGD with momentum, so and so, so and so, so and so. VLLM, efficient platform for inference and serving local LLMs, including an OpenAI compatible AI server. Okay, let's look at that as well. Okay, wait. I'll look into this later on. Let me read Gemini's response. Yes, exactly. Llama C++ is fundamentally a library first, and the command line tools you run, such as Llama CLI and Llama Server, are just thin executable wrappers built on top of it. Because it's a modular engine, you can treat it like a software building block. When you move past just typing commands in a terminal and start writing code against its actual API, the possibilities expand dramatically. What can you do with the Llama C++ library? What can you do with Llama CPP as a library? When you integrate Llama CPP into your own software, you get granular control over the lifecycle of an AI model. Hot swapping and dynamic cache management. Instead of closing a program to load a new model, your app can dynamically load and drop GUF files from memory on the fly. You can also share a single model's memory across multiple user sessions simultaneously, then state saving and loading. You can pause a massive chat session, serialize and serialize the exact state of the model's brain to a file on your hard drive, and reload it instantly later. This completely skips the time-consuming process of having AI reread a long chat history, um, which is the pre-fill phase. Okay, then structured JSON output slash grammar constraints. You can force the model's raw math engine to only output structurally valid JSON, SQL, or specific code syntax by feeding a GBNF, GGML Bacchus NOR form grammar directly into the sampling engine. I haven't understood that. I think I'll look into that later. Then custom speculative decoding. You can load a tiny draft model, such as a one A 1B model. I remember when billion was considered small. Sorry, when billion was considered big, 1 billion was considered big, and now we have like multi-billion models. That's crazy, dude. Now we've got even like 10 billion, 20 billion. That's insane. Oh, yeah, 70 billion. That's another example. Um, you can load a tiny draft model and a massive target model into the same code workspace. The tiny model guesses the tokens quickly, and the big model instantly approves or corrects them, speeding up the text generation by up to 2 to 3 times. Then custom tool calling. You can intercept the logits mid-generation to detect what a model wants to call, when a model wants to call an external API or database, pause the model, fetch the real-world data, and inject it back into the model's context. Speculative decoding is the future. It seems like it. It seems like a very useful feature. Like being able to, it's saying the tiny model guesses the tokens quickly, and then the big model instantly approves or corrects them. I would definitely be interested in exploring how that's working because I can see that being useful. At the same time, I need to understand how one model telling another model, um, how one model correcting another model's token generation is speeding things up when you already have that other model running. But like, could it be that the other model is not entirely running, if that makes any sense? Like, there's only a certain part of the bigger model, I mean, there's only a certain part of the bigger model that's running, which is what's helping correct the smaller model, and thus you're able to run this very small model and also the bigger model, but like a very small portion of the bigger model. And so you're consuming much less resources and still getting a decent output. Actually, let me ask this question. Hey, can you explain how the following works? Tiny model can be the same as the main model style or different. Okay. Um, I didn't fully get how that changes things. Okay, let's wait. The next gen is D-Flash, where you use a diffusion model to generate the draft. Yeah, so what you said is how MTP works in Quen. Wait, what is MTP? Multi-token prediction. Okay. All right, let's see what Gemini said here. You've actually got the core concept down perfectly. It's a brilliant technique. Generating text with massive AI models like a 70 billion parameter model is notoriously slow because the model has to run its entire massive neural network for every single token. Um, for every single token it produces. Speculative decoding completely flips the script by turning token generation into a guess and check teamwork exercise. Here is exactly how that process plays out behind the scenes. The draft model speculates. Instead of asking the 70 billion heavy lifter to generate text token by token, the system hands the prompt to the tiny draft model. Because the 1 billion model is lightweight, it can run incredibly fast. It is asked to look ahead and guess the next few tokens, say a sequence of 5 tokens in a row. Example, if the prompt is the sky is so and so, the 1 billion model might quickly spit out blue and filled with clouds. Then the target model validates. This is where the magic happens. The system takes those 5 guessed tokens and feeds them all at the exact same time into a massive 70 billion target model. Large language models are much faster at checking a sequence of text all at once. Wait, the 5 guessed tokens. Okay, okay. Large language models are much faster at checking a sequence of text all at once than they are at my God, generating it one token at a time. The 70 billion model evaluates the mathematical probability of each guessed token in the sequence. So it's a different set of actions that's happening. One is when it's generating the data, and the other is where it's validating the data. Okay, the issue is that when you have extra decoding layers to do the draft, the model has to use them for prompt processing. The draft model can predict a bunch of tokens, and the big model can choose to accept them if it agrees. I never quite understood how it can know if it agrees during validation without doing the calculations itself. It's faster if you only guess one token ahead. All right. Um, Large language models are faster, so and so, so and so, so and so. 70 billion model evaluates the mathematical probability of each guessed token in the sequence. Um, Acceptance and correction. I guess this will answer the question about um, how it can know if it agrees during the validation. Let's see. The target model looks at the chain of guesses and decides whether it agrees or disagrees. If the guesses are correct, the 70 billion model agrees with all 5 tokens. It accepts them instantly in a single computation step. You just generated 5 tokens instead of one. Okay. If a guess is wrong, if the model agrees with blue, so and so, so and so, so and so, but then decides that width should actually be off, it will accept the first 3, correct the 4th token to off, and discard the rest of the guess. Why it saves so much time. Even though the tiny model makes mistakes and some guesses get thrown away, the drafting process is so cheap computationally and the parallel checking is so fast that the net result is a massive speed up. You can get the exact same quality output of the 70 billion model, but at a fraction of the time, frequently hitting that 2 to 3x speed increase you mentioned. All right, let's find out. Okay, how exactly does the model, how exactly does the 70B model uh, decide whether it agrees or disagrees? what calculations are taking, I spelled calculations wrong, calculations are taking place that would be different from if it were, I know for sure there are different like calculations that are taking place for validation and for generation. I'm guessing, okay, if there's validation code, if there's a validation step within the model, I'm guessing under usual circumstances, the 70 billion model would both generate and validate its code. I'm just taking a guess here. So if that's the case, then maybe all we are doing is using a different part of the model. We are generating the tokens from a smaller model and then having the larger model's validator, whatever the validator is, we are having the larger model's validator validate these tokens. And because the validator of the bigger model would be better than the smaller model, so that's why we are able to get high quality output. But I guess that's iffy, isn't it? Because the 1 billion parameter model isn't necessarily always going to produce the best output. So maybe you might need a couple extra tries, but then maybe that still ends up being faster. I'm not sure. What calculations are taking place that would be different from if it were generating the text or the tokens itself? Um, does it do validation when it generates its own tokens? Is it basically that we are just skipping the generation and only using the validation um, part, I guess, the validation part of the model, and thus getting this speed up? To understand exactly why this is faster, we have to look at the math happening under the hood of a transformer model. You hit the nail on the head with your last question. Yes, we are essentially skipping the repetitive generation loop and leveraging parallel validation. But the secret lies in how LLMs calculate probabilities. When an LLM processes text, it doesn't just output a single word, it outputs a probability distribution that is a list of percentages for every possible word in its vocabulary. Oh, wow, that's crazy. So for 70 billion parameters, would that be 70 billion probabilities? No, it says for every possible word. Okay, I'll look into that later. Let's look at what happens when the 1 billion model guesses a sequence and we pass it to the 70 billion model. The standard generation math, if the 70 billion model was generating on its own, it has to work auto-regressively one by one. So if the input is the sky is, then you run the 70 billion model, you output blue, which takes 100 milliseconds, and then you input the sky is blue. So now we are adding the word that we generated previously. And then you run the model again, and then it outputs and, which takes 100 milliseconds, and these two tokens in total took 200 milliseconds. The speculative validation math. The 1 billion model guesses blue and then the 70 billion model is given the entire sequence at once, which is the sky is blue and then because of how transformer networks are built, the 70 billion model can calculate the probabilities for every position in the prompt simultaneously in a single forward pass. It computes position one, which is after is, and position two, which is after blue. So for is, what is the probability of the next word? The model's math says blue has a 90% chance. Since 90% is high, it accepts the guess. Then for position two, after blue, what is the probability? It says 85% chance. It accepts the guess. Because this happens in parallel, running the 70 billion model once takes the same 100 milliseconds, whether it's looking at one token or five tokens. The total time spent for two tokens, 100 milliseconds. The decision rule. The target model uses a sampling algorithm. If the draft token falls within the acceptable probability threshold calculated by the 70 billion parameter model, it's approved. If it's a wildly low probability token, it's rejected. Does it do validation when generating its own tokens? No. When a model generates its own tokens, there is nothing to validate because it's the ground truth. Oh, okay, I was wrong about that. It doesn't do validation when it is generating its own tokens. How is the same model then being used to validate some other model's output? Wait, when the 70 billion model runs normally, it calculates the probabilities, picks the best token, and immediately appends it to the prompt. It doesn't double check itself because its own output is, by definition, its best guess. The core paradox. It feels counterintuitive. If the 70 billion model still has to look at the tokens, why is it 2x or 3x faster? The bottleneck in modern AI generation isn't actually raw math power, it's memory bandwidth. During standard generation, to generate one simple token, the GPU has to load all 70 billion parameters from its VRAM into its processors. It does a massive amount of memory transferring just to just to compute a single word. This is called memory bound. This is called being memory bound. During speculative validation, the GPU loads these 70 billion parameters into its processors once, but it uses them to verify four, five, or six tokens simultaneously. You are getting much higher higher matrix multiplication efficiency out of the GPU hardware. You fetch the massive 70 billion parameter model from memory one time, but you get multiple tokens worth of work out of it. I've kind of understood this, not fully. Okay, depends on how the decoding works. Sometimes it's a smaller model. On Quen, it's an extra decode head that gets bolted on. So it just runs through a small part of the model to predict, then verifies with the whole model. I feel like this would make more sense to me once I've actually done this myself. Because right now I'm just like trying to imagine the thing, but I'm not able to fully get it. I'll get there though. I'm going to be studying LLM architecture soon, hopefully, through the Hugging Face course. Hopefully soon. Okay, now, um, I do need to end the stream, unfortunately. The good news is we got a good like 2 hour and like almost 15-minute stream in, which is awesome. I managed to start the stream earlier today. I'll try to start it even earlier tomorrow. This is actually great. This is much better in terms of timing than starting late. I'll see. Maybe I might record another vlog tomorrow. For today, I need to finalize my Inquire and Clap learning and finally start working on the, what do you call it? The knowledge base. What was it called? KB tool. The knowledge base KB tool. Um, yeah, yeah. Zaina, thank you very much for stopping by and chatting and hanging out and stuff. Anyone else who might have been lurking in the chat, thanks for hanging out. I'll stream again tomorrow. We're going to continue with more Rust stuff. Maybe I'll continue working on the KB tool. Maybe I will. I don't know what all do we have in our list over here? Hold on. What all do we have in the stream map? Oh yeah, we have to get back to Git branching. I forgot. Yeah, we have to get back to Git branching. Use GitHub Copilot to understand Western. Yep. Okay, I have to do that. The Zola stuff, that would be for, okay, I have to finish the knowledge base first. First, I have to finish the knowledge base. After that, once I've finished the knowledge base, I can start working on my dot files repo because that requires me building a tool as well, specifically a tool that can read a toml file and fetch, files and directories and then update the entire repo with that. Um, but yeah, yeah, okay. That's going to be it for today's stream. I hope you guys have a nice day, and I'll see you all next time. Peace.